Thank you. Thank you for the invitation. It's a pleasure to be here, and especially a pleasure for being the first speaker in the first day of working air conditioning. It's really a revolution in this in this whole week. And okay, so let me go to the topic of my talk. I want to start with the three pictures. Actually, I should have put some line between the first one and the other two, because in some sense the first and the other two belong to different categories. I would also ask Simon if he can recognize the first one. He can? Yes, so the first is, just for fun, I put here a triangulation of the Heisenberg isoperimetric setting, so the solution in the discrete setting of the isoperimetric problem in the Heisenberg group. But we are not talking about isoperimetric problems in sub-Riemannian geometry, not at all. Just for showing you, so this category of triangulation or triangulated object that I would like to call, say, highly or relatively highly structured discretization of surfaces. And another kind of objects, point clouds, and pixel or voxel type, volumetric type approximation of object or geometric objects. The starting point of this research, which, sorry, I was too fast. It is in collaboration with Blanche Buet and Simon Masnou from Lyon. We had some motivation for this research, essentially related to numerical methods, considering finding possibly new numerical methods for suitable for geometric variational problems. And the idea was also to be as more general as possible in some sense. So considering different types of discrete surfaces and try to deal with them in a sort of uniform, unique or unified way, without particular restriction on, for instance, dimension and codimension, even without having some a priori constraint or knowledge on the topology of these objects, on even no orientation. And so possibly we would like to consider even non-orientable objects, surfaces. And we also would like to allow singularities. What does it mean? Maybe singularities not in the discrete object, but in the limit object that the discretization would try to capture, to approximate. So we want to allow singularities because, well, for various reasons, I like, for instance, bubble clusters problems, so isoperimetric type problems. And in those problems, singularities arise quite immediately, so even in smaller dimensions. So I want to consider surfaces, so objects, to be approximated which have singularities, so generalized surfaces. What I want to do is to define, to try to propose some discrete version of generalized quantities like curvatures. And in this talk I will mainly focus on mean curvature, so generalized mean curvature. And another point is the following. It's a kind of point of view. So I don't want to makes some sort of prior reconstruction of a surface in order to recover the curvatures, so, or this generalized curvature. I would like to do something more direct, so recover these features, curvatures, without reconstructing some nicer geometric object. This is my idea. So just to mention some so the literature about discretization of surfaces is really huge, and I confess that I'm not so expert and relatively new to this topic, and also to numerical aspects of connected with the geometric measure theory. But so I just put some references. I will be probably not exhaustive. I would say absolutely not exhaustive, and so please forgive me if I am forgetting some people, some relevant contribution to this theory. So the idea is that there is, in the context of discrete differential geometry, there is this already quite significant knowledge about how to provide the discrete equivalents for this geometric notion of curvature and quantities related to curvature, or to geometric features of surfaces. And so there are tools originally tailored for, say, smooth objects that have been reformulated for these discrete settings. For instance, recently I was quite fascinated by this discretization, which have these properties of preserving some invariance with respect to transformation groups. It's an interesting paper by Bobenko-Offerman and Springborn about way of discretizing, for instance, minimal surfaces with a sort of suitable disk packings that have this invariance property with respect to transformation that preserve the minimality of the surface. So really interesting new ideas in this discrete differential geometry context. And also for the what concerns energies on surfaces, or so variational problems involving surfaces, so it is very interesting to consider discrete counterparts of continuous energies in these settings. Then, well, of course, to do this, to develop these theories, typically a certain structure on the discretization must be required. So typically you use triangulations or nets of points where you know which point is close to which other point. So you know a structure which is also a sort of topological structure that a priori you have to fix, to impose, in order to do your computations, your reconstructions. And for instance, from the point of view of limit objects which admit singularities, is not fully taken into account, this problem, and so that typically one is interested in reconstructing, in discretizing smooth objects, something that in the limit will be smooth. On the other hand, there is also another sort of community, within the, say the discrete differential geometry group, another community which is interested in sort of discretization of surfaces that comes from data, for instance, various type, for instance, medical data, medical imaging, and data acquisitions that have to do with the shape modeling and graphical rendering, And here you essentially you have something which is less structured. It's, for instance, in the first example, it's a dragon that you will see even later. You have a huge number of points that more or less are placed on a surface of this, on a boundary of this dragon. And you see something, you see a shape, but it's a shape made by points, dots. And you don't have any connection between one dot and another dot. You don't know who is connected with who in any sense. You know only the distance, okay, but this is not really a strong topological information. And there you have pixels or voxels that in some sense show you this shape, or the boundary of a shape. So here in this context, instead you need really some way of processing this data possibly in an efficient way without, say, if you want to reconstruct some features possibly you would like to find some direct, some straight way of getting to the data, to the features. And here, for instance, what, in my opinion, is mostly done is, in any case, first to do a sort of prior reconstruction of the surface, and then from that surface you get something. It is reasonable because for, say, cutting out some noise in this data, which could be affected by noise, you maybe are very often forced to reconstruct some surface which fits, which regularizes this noise and throw away the noise. For instance, these techniques and this moving least square reconstruction means that you are trying to find a surface which fits your data with some procedure, some sort of fixed point procedure and energy minimization. But still, first you want the surface, a more regular object, then you infer some geometric property. A weaker approach that I found very interesting is the one based on the so-called curvature, or better, curvature measures reconstruction via offsets of distance type functions from compact sets, or maybe sampled compact sets. You have some sampling of compact sets, and you consider distance function from these sets, and you look at the offsets, so tubular neighborhoods. And from the offset, you can reconstruct information on the so-called curvature measures, considered by Federer, but the theory starts from Steiner and really old, about the volume of tubular neighborhoods, Steiner, Weil, Minkowski, and so on. And this theory has been generalized after work by Fu, who started essentially by this idea of normal cycles introduced by Wittgen and Zelle. And with this theory of normal cycles, here we are in context of currents in higher dimensional spaces. So you see, you look at the normal, the Gauss map, and you generalize the Gauss map in the sense of currents, more or less, very vaguely. So based on this theory, there are several interesting approaches in which you can reconstruct, even from point cloud type data, so very maybe affected by noise, you can reconstruct information on the curvatures just by using these distance type functions. So here I put a list of people, but probably I'm missing many people. So that's my our claim is that essentially, if you want to deal with very low structured discretizations, this discretization gives you information about where, essentially, where the mass is distributed, and possibly up to some reconstruction of approximate tangent planes or approximate normals, maybe also where these tangential information are distributed. So essentially, mass and tangents. So varifolds seems a quite natural object to be considered in order to use these essential minimal informations. And up to now, what we found is that varifolds have not been really or strongly applied and used in the discrete setting. There is a paper by Sharon and Trouvé where they use varifolds for problems coming from diffeomorphic image registration. But apart from this paper, I really don't know many other papers where varifolds are used. And so the idea is, okay, there is a theory of varifolds, which is quite old now, so it started in the 70s, and maybe we can use it and maybe try to discretize this theory and go to find these discrete varifolds, possibly. So let me recall very briefly what a varifold is. So you have here I'm really simplifying the picture. I don't fix an open set, general open set. I take Rn, just to avoid some technical complications. So what is a k varifold in Rn? I take k less than n. So it's a random measure on Rn times the Grassmannian of k planes in Rn. And so it's a random measure, positive random measure. And from this measure, you can define the so-called mass or weight measure, bar v. And this is essentially the push forward by the projection on the first factor, so on the spatial, on the Rn of the varifold measure, which is on the product. Okay, so you have the push forward by the projection, and okay, this is a very general definition, but in this cluster you can find many objects, and in particular you can find the so-called rectifiable varifolds, so varifolds which are given essentially by a rectifiable set, like this union of sheets meeting in some way with locally finite k measure, hk measure, and coupled with the multiplicity function theta that could be the real or integer valued. In the case integer valued, we say that the varifold is integral, right? And how it is defined? It is defined as its action on test functions defined on the product Rn times g and k is just this one. But we have already seen this definition and this in the lecture given by Ulrich Menne. So I'm just recalling something. Okay, so there is a very nice operator defined on varifold. It is this so-called first variation. The first variation is a linear operator continuous with respect to the C1 topology on C1 vector fields with compact supports, and it acts in this way. So essentially, you take a vector field, and the delta v of this vector field is the integral of the divergence of the vector field with respect to the plane, the k-plane S, integrated at the point x, integrated in the measure dvxs. Okay, so this is a definition. And what is this first variation? Well, it is, first of all, this is quite important, a vector value distribution of order 1. So you can plug in, feed to, say, the first variation C1 vector fields with compact support. And then where does it come from, this definition? Well, it comes from the, say, the differentiation of the, say, the push forward of the varifold v through a diffeomorphism generated by the field y. You take so the mass of this push forward vector field, and you differentiate with respect to t. So formally, what you get is the first variation of the mass, so this operator. And indeed, there is very precise characterization in the smooth case, when M is a smooth manifold and V so is a vector field, so is a, no, sorry, when V is the rectifiable varifold associated with M and density 1, then what you get from so the action of this first variation is exactly by the divergence theorem of manifold is given by duality by this term here, this cross product, and this H is the so-called mean curvature of the surface. So everything is quite classical, well known here, mean curvature vector. And more generally, as soon as you prove that you have this extra property that this is not only a distribution but is a vector valued measure, so if it is a vector valued measure, a radon measure, then you can decompose it in say, an absolutely continuous part with respect to the mass, and this gives a vector which morally is the mean curvature vector, and plus some singular part, the boundary of the varifold, as Ulrich Menne said in his talk. Okay, so we can define, up to this condition, we can define the so-called generalized mean curvature of a varifold. And okay, so let me recall two classical results on varifolds. The first is the so-called rectifiability result, and it says that if as soon as say delta v is a random measure, so its total variation of the first variation is locally bounded random measure, and if you have a bound on the upper density, this lim sup here, the upper density, so the upper density is almost everywhere positive, then what you have is that by restricting the varifold to this set, which is in some sense the support, not really the support, but it's a part of the support of the varifold, then this restriction gives you a rectifiable k-varifold. And okay, this is the rectifiability theorem. Then we have another theorem, compactness, where you consider a sequence of rectifiable k-varifolds with a lower bound, positive lower bound on the density, such that their say, total mass plus total variation of the first variation is uniformly bounded along the sequence. Then up to subsequences, these weakly star converge in the sense of random measure on the product, the Grassmannian, to a limit varifold which is rectifiable. And you have also, by functional analysis essentially, you have this property of lower semi-continuity of the total variation of the first variation. And an important property, also quite tricky, quite involved to be proved, is that if you start with theta e integral, so integral varifolds, then under this assumption you get not only rectifiability but also integrality on the limit. So these properties are proved in the famous paper by Allard in 1972. And so let me go now to this setting of these discrete varifolds. So discrete varifolds are what? Well, I want to explain by just examples. I take here in the plane, for instance, a union of segments, these black segments. Each segment defines a tangent, a line, and so and also it has a certain length. So I can say canonically associate with this polygonal one-dimensional set in the plane a varifold, which is rectifiable, okay, and which is essentially the sum, the finite sum of the H1 measure restricted to this the segments, tensor product with the delta, Dirac delta in the Grassmannian at the tangents, okay? So this procedure essentially works for any even higher dimension and codimension, so any polyhedral set can be endowed with this sort of canonical varifold structure. And similarly, we can define a k-varifold structure as soon as we have a set of points together with tangents at each point, tangent spaces at each point. Just the same definition. So what you get here is a varifold, okay, but not so nice varifold, because you very quickly realize that this varifold is not rectifiable, first, not rectifiable, and its total variation is just a distribution, it's not even a measure. So here, essentially, one is stuck. So, I mean, one says maybe, okay, varifolds are not good for doing anything in this situation. And the similar, but yeah, slightly different, but essentially equivalent situation is when you take volumetric varifolds. So you have a discretization of the space, and you do a similar procedure. You associate to each piece of this, to each cell, some mass that you can write in terms of the Lebesgue measure restricted to that cell. And so similar definition as before. But what you get again is not a k-rectifiable varifold. The support is n-rectifiable, right? And typically what happens here is that the total variation, which may be finite, locally finite, when you fix the mesh, can have problems when you refine. When you take a finer and finer mesh, you can have, say, sort of spurious curvature or singular curvature terms that make this total variation blow up. So even in this case is critical, poses problems. Yes?
So pk is always k-dimensional in this definition and in the one before, and just you attach it to something in space which is of a dimensionality.
Yes, 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 exactly. 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 So, which is what I want to say first is that, okay, at least with these objects, with these discrete, say, varifolds, you can do some approximation quite reasonably. And in order to do approximation, it's better to define some notion of convergence. So weak star convergence is, say, sort of first important definition. And I want to use also this different notion, which has to do with the distance. The so-called bounded Lipschitz distance or flat distance, which is a, say, a Wasserstein type, one type distance. Not exactly, it's a sort of variation of the one Wasserstein distance. And you can consider it when the two varifolds have a finite total mass, because otherwise there can be problems. And, well, there are relations between the convergence in sense of weak star convergence of varifolds and the convergence with respect to this bounded Lipschitz distance. So with these tools, you can prove some approximation. You, for instance, you start with some surface or curves in this picture, and then you discretize it in a way that is maybe the most naive way you can think. You just look at which squares intersect the curve. You measure the distance, the length inside each square, and then you define according to what is captured by each square. You define a discretization. So essentially, and this kind of construction can be done in order to produce point clouds, because as soon as you have this volumetric varifold, then you can substitute it with a point cloud. For instance, you take the centers of the squares and you define, starting from this, a point cloud. And there is also a reverse procedure. Essentially, the two representations are more or less similar. So what you have is this fact, which requires some conditions. So if you have a rectifiable k-varifold, and if you take a mesh of mesh size delta I, and you make the construction as before, then what you can prove is that this construction, as the delta I goes to 0, the mesh size goes to 0, then you produce a sequence of discrete varifolds that weakly start converge to the limit varifold. And then you can have something more quantitative as soon as you require some regularity of the varifold. And the regularity is not actually so strong. Well, it's quite strong, but not so strong if you are thinking of, say, problems, of variational problems involving surfaces or objects that at the end will give as solutions a certain type of sets. For instance, these M epsilon delta minimal sets, in I don't want to define them. There is a regularity theory for them developed by Taylor, and with also some news due to David, so an extension to higher dimension up to some careful, say, hypothesis to be put in for going to in higher dimension for two-dimensional minimal set in this sense. And the requirement that here is written, so the existence of a decomposition of the mesh into two parts, parts in which you have a sort of order regularity of the tangent planes, uniform order regularity, and then on the remaining part a condition of smallness in the sense of the mass of what is left. So with these properties you produce a quantitative estimate with the bounded Lipschitz distance of this type. Okay, so this is not particularly complicated. And but then we go to the first variation. What about the first variation? Because with the first variation we recover curvatures. And can we do this recovery procedure here? So there is a problem. There is a problem, as I said before. There are spurious terms when you refine the discretization, the mesh, that creates a blow up in the first variation, in the total variation of the first variation, and this is bad. But then one can have a posteriori very simple idea. It's a very simple and naive idea. Okay, you have assume that you have this pixelization of something which should be nice. Maybe you are looking at this pixelization from too close. And so you see pixels and you see they are too big. So that's the problem. You should go a bit far, and maybe essentially your objects will look like something nicer. So it's just a matter of choosing the right scale in some sense. So curvature, measuring curvature means also to fix some scale with some criterion or criteria. And so fix a scale. Right? And well, actually, what we fix is something more than a scale. We fix a convolution. We do a regularization. But in which way? In this simple way. We take a convolution kernel. We need just W1 infinity with some standard properties. And then we define the regularized first variation, the epsilon regularized first variation, actually the rho epsilon regularized first variation, in this way. So this is just, let me say it in these terms, it's a spatial regularization of the varifold. It is not the spatial regularization of the mass. Because if you do this second regularization, this is not going to work. So this is essentially the problem. So you do a spatial regularization of the whole varifold. And this, in some sense, has the effect of spreading somehow the tangential information. So this is important. And in a similar way, well, let's say, by sort of analogy, we can define this quotient. So the convolution above, and then here we convolve the mass. And then we take the ratio. So this gives something that would resemble the generalized mean curvature. So this we call the epsilon regularized generalized mean curvature, GMC. Okay, what is nice is that these objects are well defined for any varifold. So you can really, you don't need, because you don't need special properties to consider these objects. And what you get as soon as the mass of the varifold is finite is that the convolution of the first variation is in L1. Maybe you do not, you don't have a bound, a uniform bound with this, but essentially it is at least in L1 of Rn. So it's a function in L1. And from the numerical computational point of view, this is very easy, convenient. Just an example. Take a point cloud, so n points with the tangent information. You compute this mean curvature, epsilon regularized mean curvature. It's a formula. Just here there is a projection, orthogonal projection on the plane, Pj. It's a formula which is very, very easy to implement. And here, I just show first, there will be not too many simulations and some other pictures, of course, but I didn't I won't show everything what we have done, also because we have some collection of experiments, but still we are, I would say, at an early stage in this experimental part, but the results are quite nice. So time permitting, we will get to some more complete set of simulations and tests. So this is what is reconstructed on this 8. So you see it as a continuous curve, but actually this is just a plot of a union of how many? 10 to the 5 points. So they are very close. So this is a synthetic image, very, very smooth. No noise, nothing. It's just for testing the definition. And what you get is something very consistent with the fact that, for instance, when you get here to this cross point, in the varifold sense, for the smooth object, in the sense of varifold, there you have a zero mean curvature. And this is precisely what is reconstructed by this discrete version. So it seems, okay, it's a very, very easy example, but it seems working on the singularity, for instance. And okay, let's see if I can, so compactness and rectifiability. So we tried, before doing a lot of simulations, we tried to understand this theory and convergence properties. And the idea was the following, has been the following: try to recover results of type compactness and rectifiability, first of all, in a sort of slightly generalized form with respect to all the Allard's results. So in which sense? Instead of starting with rectifiable objects, you start with these more general objects, and then you want to find conditions in order that in the limit you get the property. So you get the compactness, and you get also rectifiability. So what we have proved is that if you assume this bound, and here you see there is a convolution of Vi with respect to rho epsilon I, and epsilon I is an infinitesimal sequence. You fix 1, and you assume that for that one you have a uniform bound. Then what you can prove is that up to subsequences you converge to the varifold in the weak star sense, and the limit varifold has a bounded first variation. But then if you now ask something more about a sort of scale-dependent density, so you fix another sequence Ri of, say, scales going to 0, such that above these scales you get a density, a lower bound above, because of course if your discretization is a discretization, you cannot go to up to 0, because then you will see something which is not good. It cannot satisfy this bound. So you have to be far, but not too far. So the scales Ri must go to 0 as well. And what you get at the end is that you prove also rectifiability of the limit varifold. So this is, I would say, a slight generalization of Allard's theorem, a slight generalization. But it is interesting in this setting. And I want to say that Blanche, before getting to this result, Blanche got an interesting, very interesting result of the same type, so rectifiability of the limit with different hypotheses. So she realized that if you use a sort of integral mean variant of Jones beta numbers, and you control these means, integral means, then you can apply a result by Hervé, and you get a rectifiability in the limit. So it's another way of getting to the same result, the same conclusion. Okay. Here is the proof, but I want to skip it because it's really simple. It's a proof with just a few functional analysis, and then at the end you apply Allard's rectifiability, because so it's not a difficult proof. It's relatively easy. I just put here for, yeah, I skip. Okay, so let me go to this issue, the convergence properties of the epsilon regularized GMC. So the ratio minus the ratio between the convolution of the first variation and the convolution of the mass. Let's see what happens when epsilon goes to 0. And okay, so first the pointwise convergence result. Take a rectifiable k-varifold with finite total mass. Maybe the assumption is not optimal, but and take a sequence of meshes with the mesh size delta I. I didn't wrote it, but going to 0. Delta I is going to 0. And take an infinitesimal sequence of scales, epsilon I, going to 0. And now fix a kernel. And here you have to require W2 infinity. So before there was just W1 infinity. Here, for kind of structural reasons, you have to take W2 infinity. Kernel, and also it is convenient. It's not clear if it is really needed or not, but the proof comes with this extra property, with a decreasing profile. So the profile of the kernel is the usual that you consider when you take a standard kernel, standard modifier. And then you take a sequence of these volumetric varifolds defined as before as the discretization with respect to the mesh. Okay, then what you can prove is the following. First, you have to assume those assumptions, you remember 1 and 2, that have to do with the regularity of the limit. So Holder estimates on for the regular part in the mesh, so Holder estimate with respect to the tangent planes, and smallness of the singular part. And if these are satisfied for some constants, then, so beta was the exponent of the Holder regularity, then first of all you have a pointwise convergence for almost all points in the support with respect to the limit mass. And then if you add another assumption, it could seem a bit strong, but generalized mean curvature Lipschitz, well, yes, it's a strong assumption, but for instance you include minimal surfaces, you include constant mean curvature generalized surfaces, so it's not so bad. Then you have a quantitative estimate. And here there is a term, this epsilon I comes from the Lipschitz property. And then there is a sort of uniformity that here, okay, so the epsilon I is just the Lipschitz property, but what is for me important here is this term. This term is a sort of asymptotical, you should understand it as an asymptotical decay of the error in terms of the mesh size and the scale epsilon at which you are computing the mean curvature, the approximated mean curvature. So and you have epsilon I squared. So it's this square that you get, and this is a structural, these are kind of structural exponents. And well, here just a comment. Why it is structural? Essentially, you get this epsilon squared and this delta I over power beta divided by epsilon I squared. Because when you make the estimate, you estimate the error, you get terms like this one to be estimated. And when you estimated them, you use the bounded Lipschitz distance, and you play with that, you scale, and what you get is a first estimate of the numerator, where you see up to constant epsilon I to the power k minus n minus 2. It's just a matter of computation of Lipschitz constants and the gradients of gradients. and times delta I, so the W2 infinity norm of rho times delta I to the power beta. And then if you use the rectifiability of the limit varifold, you have an asymptotic behavior of this convolution, which is epsilon I to the power up to constant to the power k minus n. So you take the ratio and you get the asymptotic behavior. Okay, so what did we tried with these notions of approximate generalized mean curvatures? We tried to apply them and to see if we could prove a gamma convergence result for, say, P-Wilmore to the P-Wilmore functional in the context of varifolds. It's for it could be seen as a sort of exercise, but well, we believe that it could have some interest, and that's what we got. So we take V, K varifold with final total mass, and then we assume that its total variation its first variation, is absolutely continuous with respect to the mass. So there is no singular part. So we have a varifold with generalized mean curvature in some LP, P is fixed, and then we define the P-Wilmore functional in a proper situation as WP of V as this integral of the P power of the mean curvature with respect to the mass measure. Otherwise, if we are not in these conditions, we say that WP is plus infinity. Okay, then by analogy, we define the epsilon version, this approximated version of the P-Wilmore functional, and this is what you could have imagined clearly. It is this. We take the approximated mean curvature, the ratio to the power P, and then we integrate so here with respect to the same convolved mass. So this is with respect to Ln, so the Lebesgue measure, because you have diffused the thing. And okay, so what you get is that in the weak star topology, or if you want in the bounded Lipschitz distance, you get this gamma convergence in the space of varifold, which is a first result, in which you essentially you look at the whole set of varifolds and not just the discrete ones. So we have also results in which you constrain, we reduce the spaces to a sequence of spaces of discrete varifolds. But first we have to prove this more general things to understand this, and then we got the other result for which are more interesting essentially with the such that you can say that you can approximate the problem in the discrete spaces. So this is instead in the varifold space. So there's the two energies in the same space. It's a simple case. So in the case P equal 1, we can prove this gamma convergence, but not to W1, but to the total variation of the first variation. This is okay. It's quite reasonable, like W. So there is, if you want the analogy of the compactness of W11 function, which is not in W11 in general, but in BV. So essentially, we have as a gamma limit the total variation of the first variation. And okay, this is relatively easy to prove. The gamma limit inequality is essentially you do the same proof as in the compactness theorem. It's not really different. It's essentially the same. And the gamma lim sup inequality is really trivial because it's pointwise. You fix the varifold, and so this is really trivial, really trivial. A bit. Some more complications come with the case P greater than 1. So here you need this sort of interpolation lemma. So you first, because you need to reconstruct the first variation in order to do that, you have more integrability and so on. So first you need an interpolation saying that if you essentially if you control the WP epsilon functionals and the mass, then you control the W1, okay? And the proof is not complicated. It's Jensen inequality. And then with this lemma, you prove the gamma convergence. Very briefly, so the gamma lim sup, is easy. Same thing as in the p equal 1 case, essentially. Same easy, just Jensen in that case. But, the gamma lim inf, it's a bit more complicated. You have first to use the lemma. Then as soon as you get this bound, you use the result for p equal 1, and then you get that the limit is bounded, because at the beginning you don't know, right, that v has a bounded first variation. You don't know. You start with bounded with respect to the epsilon functional, and then you have some weak convergences telling you that you can apply essentially a standard lower semi-continuity result for functionals defined on measures. You can find on Ambrosio Fusco-Pallara's paper, for instance. Book, sorry. And with this result, first, okay, you prove that this is absolutely continuous. You get this property, so you have a generalized mean curvature, but you have also integrability at the power p of the generalized mean curvature and lower semi-continuity. So essentially, in this way, you recover the gamma lim inf inequality. Okay, here I want to be very quick, so I don't enter into details about the say more interesting case in which we fix also the approximation spaces, a sequence of discretized spaces, so meshes and blah blah. I just tell you what happens. There are some modifications, some little modifications. There is a point that for now is a bit technical. I will tell you in a while. A bit technical, and where you have to choose the kernel, choose a shape, a sort of property of the kernel, which is something strange. Maybe it's just a technical point, not substantial. So essentially, the gamma lim inf, okay, you have already done it. The point is the gamma lim sup, so the approximation. And in the approximation, you need essentially more regularity of the limit, and because otherwise some estimates could go wrong. And what you get, yes, so some regularity in the spirit of the two hypotheses that I stated a couple of times before. And then what essentially you get it, but in the case p greater than 1, there is this technicality leading to a sort of condition which makes the proof very natural, just a Jensen inequality, then after this choice. And you have to choose the kernel rho in such a way that, so the kernel is decreasing, so minus rho prime is less than c times rho to a power alpha, with the alpha between, you must choose it between 1 minus 1 over p and 1. So there is this technical point, but we cannot say it is structural, not at all. Okay, so let me show you in the remaining time some numerical tests. As I told you, I decided not to put a lot of tests, also because yesterday I had a problem in finding the files, so I made a choice with what I could find in the directories. Sorry, it's my fault. But I think that they're not too bad, so I would like to conclude with this. Before showing you this test, I want to tell you something recent. So it's a matter of a couple of weeks ago. Something recent that has to do with, say, something strange that Blanche discovered just doing tests with various kernels. So she discovered a strange property of a very simple kernel. So we used for some tests the 10th kernel like that. And then Blanche, one day, we don't know why, decided to take the taint and reverse it. And reverse, and then take it 0 outside. Okay, let's try, but no, the theory is not working for this. This is not Lipschitz. No. What happens here? Okay, and she did the computations, stability, speed, something magical with respect to all the other choices that we made of kernels. So we were very puzzled. We didn't understand this fact. And so at some point, we tried the computation. So let's take some, first a sphere, then with a quadratic form, so to have different curvatures, different principal curvature, quadratic form, you look at the graph, and then you try to do the following exercise, which is a sort of corrector term, a way of adjusting the curvature, the approximated curvature, in order to get the true curvature in some for some special smooth object. So it's sort of exercise. And then, well, it came out this strange thing. So first, we had to generalize the definition of the approximated mean curvature. So instead of using just one kernel for the numerator and for the denominator, we tried to use, because this was the way of interpreting Blanche's idea or discovery. So the way was to use different kernels and to adjust just a factor with the right factor. So essentially, you can do again the theory, and everything works more or less in the same way. But now you have more freedom. You can choose the pair of kernels. So for instance, you can fix rho and then ask which is the best psi for that rho. And okay, so the surprise that at some point there is, when you do this analytical computations, you find something which is 0 in some integral mean sense by integration by part thing, something that is 0 only in the integral sense, on an interval, and then you see it and you say, but what if not the integral, but the integrand is 0? So you force some sort of extra condition. So the integral is 0 for any choice, for any pair, but forcing the integrand to be 0 for any value of t, so t running from 0 to 1, forcing inside the integral, so the integrand to be 0, you get to this special so-called natural choice for psi with respect to rho. So if you decide who is rho, then it's analytically good to choose psi in this way. And this is precisely what Blanche discovered with that reverse tent kern. So this very, very surprising thing. Still, we don't know why, from the numerical, it's not completely clear why in the numerical setting this is so good, because it's really good, really improving not only for a very special curvature, only for circles, no, for and in any dimension and codimension. So it's really universal in some sense.
Take rho equal to minus 0 prime, what happens? Yeah, it's kind of
You mean rho equals to self? Yeah. All right, that is a good idea. We must try the we must do the It's not completely supported, but yeah, but okay, truncate. I don't know. Yes, interesting. And so let's say if you take this special pair, assuming that you fix rho in advance, then you call this pair a natural kernel pair. Just the first name that we. 1 minute. Sorry. So what I say, and here it's just one of some tests. Can you see the yellow line? So here it is a flower, varying curvatures, discretization with like point clouds, and So a choice of kernels, the first 3 are row-row pairs. Okay? This one yellow is the natural pair. So in this case, it's the 10th kernel, but you can use maybe smoother things, and they really all go like that. Even in cases where you have very high curvature, so the error, this is a log-log scale of the error. The error is, so it's decaying as the theory more or less predicts. So up to some, but essentially this is the thing. And let me, okay, time running out. A mesh of triangles, it's just experiment. Take just the vertices of the triangulation, then you have a cloud of points, and then this is what the method reconstructs in some test that Blanche did for this dragon surface. And this is the reconstructed, say, absolute value of the mean curvature. So it seems reasonable. And then, okay, maybe there are errors, because the surface is very complicated. But the features that, if you compare this result with the many results that we find in the literature, really, well, it seems reasonable. I don't want to say that it's the right thing, but reasonable in this complicated situation. So thank you very much. Here are some details, some possibilities, but I want to stop.